Hi everyone, and welcome to Learn Uniform Circuit Lower Bounds and Provability in Bounded Arithmetic at FOCS 2021. I'm Marco Carmosino, and I'll be presenting this joint work with Valentine Kabanets, Antonina Kolokolova, and Igor Oliveira. Let's start with some questions about complexity theory and metacomplexity theory. The first question is just P versus NP for circuits. So does the Boolean satisfiability problem have polynomially sized, so efficient, non-uniform Boolean circuits? Do efficient circuits solving this problem even exist? We conjecture no. We conjecture that satisfiability is not in P-poly, and this is a lower bound conjecture. A meta question about this conjecture and the problem itself is, if that lower bound conjecture is wrong, how hard will it be to refute that? And note that we want a formal answer to this question, not just people have tried very hard for a long time to build efficient SAT circuits. We can't answer these questions yet. If we could, the title of the paper would be different. So let's pass to some easier questions about meta-complexity theory. Question number 1. Does NP have quadratic size non-uniform Boolean circuits? So this is an even more extreme question than the question on the last side, right? We're asking, does every single language in non-deterministic polynomial time have a quadratic size Boolean circuit? And we really conjecture that this is false, that NP has to have languages that can't be decided by deterministic quadratic size circuits. The meta question here, again, is if this lower bound conjecture is wrong, which would be very surprising, how hard is it to refute? Now we can formally answer this meta question. We can say that there's a natural theory, T, and by natural I mean that this theory is expressive enough to prove the PCP theorem, a deeply non-trivial result in complexity theory, such that this theory does not prove NP has quadratic size circuits. So that's good, that's progress, because that says that even if we are very, very wrong about the expressive power of NP versus quadratic size circuits, then at least we know that techniques outside of this reasonable and powerful theory will be required to prove that absurdly efficient circuits exist. Okay? So let's dig into the sense in which this is formal. And that means that we're going to need to define a theory. We'll define those by analogy to complexity theory. So let's step back for a moment and talk about complexity and metacomplexity. Okay, so in straightforward complexity theory, our tasks are usually decision problems. Some of our favorites are Boolean satisfiability or graph reachability. Our measures are computational complexity, so algorithm runtime, number of random bits, circuit size. In metacomplexity or proof theory, our task is to prove theorems, not to decide problems. And generally, we'd like to prove theorems about the correctness of algorithms or the existence of circuits. Our measure is going to be some kind of quantification of reasoning complexity. And that's less clear starting from a complexity theory background. So let's start formalizing this. When we prove something, we start with good axioms, we combine that with some inference rules, and we can get to a universe of all derivable theorems from that set of axioms combined with those inference rules. Just like a complexity class is a collection of decision problems, a theory is a collection of derivable theorems from axioms and inference rules. Good, so that's what a theory is at all. What's a natural theory? So our big ask on this slide, relating complexity and metacomplexity, is can we bootstrap our understanding of reasoning complexity from computational complexity? Are there theories that are sort of in a nice one-to-one relationship with complexity classes? Absolutely yes, and they are called bounded arithmetic. These are natural theories derived from complexity classes. So for example, we've got VPV derived from deterministic polynomial time. It proves the PCP theorem. And we've got VAPC1 derived from randomized polynomial time, and it proves the correctness of bipartite perfect matching algorithms in RNC2, also very non-trivial. This is a long-running research program started by Cook in the 70s, extended by Buss, and by Kryajek with two wonderful survey books in 1995 and also 2019. Bounded arithmetic continues to develop a logical path towards separating NP from co-NP by separating associated logical theories, and it is capable of formalizing precise barrier results, right? Because instead of saying that a proof technique that looks like this, say in relativization, it can say, okay, no proof that can be formalized in the following theory can separate these two complexity classes, say. And bounded arithmetic was the inspiration for the famous Rasbarov-Rudich natural proofs barrier from 1997. Okay, so that's a little bit about the theories and the program. Let's give a very thumbnail sketch of a definition of VPV. VPV has symbols for all polytime computable functions, axioms that allow it to do polynomially bounded induction and thus mimic a p-time Turing machine, and it has polynomially bounded quantifiers. So whenever you do existential or universal quantification, you are not allowed to quantify over objects that are too big to be expressed. And the major feature of these theories that we're going to exploit in our work is what's called witnessing. Witnessing captures our human tendency to produce efficient and constructive arguments, that is, to almost reason implicitly in theories like VPV. Witnessing says that if you have a bounded arithmetic proof of the existence of some object, you can extract from that proof an algorithm that constructs the object. So to be slightly more formal, let's suppose that VPV proves for all x there exists y such that r of xy. Now, because VPV proves this, the quantifiers are bounded, they're not too big, and that predicate R is going to be an efficient polynomial time predicate. But let's zoom in on this existential quantifier. As stated, this statement just says Y exists. It doesn't say we can find it. But because of the witnessing theorem associated with VPV, there is a polytime Turing machine M that, given any X as input, prints out the Y that satisfies this relation. Good. So that's a whirlwind tour of bounded arithmetic. Now, let's zoom in on the types of theorems that we want to study today, circuit upper bounds. In particular, we'll look at saying that P collapses to quadratic size circuits. So, we'll say that VPV proves that P is contained in quadratic size circuits if for every function in P and for some constant, VPV proves formally for every n there exists C such that C is a size little c times n squared circuit, where this is a function that also checks that C encodes a valid circuit, and for every x is an input string of length n, the circuit on x agrees with the function on x. So this is certainly a VPV sentence, right? Because circuit size testing, circuit evaluation, and function evaluation for any function in FP, they all have function symbols in VPV by definition. Further, this sentence has some nice robustness properties. The choice of the algorithm, the particular function symbol to represent every language in P, doesn't matter at all. So this is how we say VPV proves that P collapses into quadratic size circuits. I'll make two remarks here. First, notice that F is quantified outside this formalization, right? Like, I'm not saying for every function symbol in the formal theorem that VPV proves. So we're saying that VPV proves an infinite collection of these sentences, one for each language in P. And then remark number two is that this is a three quantifier sentence. On the previous slide, where I gestured towards a witnessing theorem, it was only a for all exists statement. This is a for all exists for all statement, because you need to say for all input lengths, there exists a circuit, and then for all input strings, it gets the answer right. Even so, even though we require a stronger witnessing theorem here, KPT found in the 90s that appealing to the Hebrand theorem, a classical result about first-order logic reducing to propositional logic from the 1930s, we can get an algorithm for uniform construction of circuits out of even these three quantifier sentences. Okay? So that's formalizing the theorems that we're studying, collapsing complexity classes into n to the k-sized circuit classes. Let's now revisit, with this more precise language, our overall meta-complexity goal. In a perfect world, we'd be able to identify a natural theory T such that T proves all of complexity theory, whatever that means, so things like the PCP theorem, de-randomization arguments, all of that, but also it doesn't prove P equals NP. Such a result is necessary progress towards P versus NP, because basically it says that P not equals NP is true inside this very powerful theory that we use to do a bunch of our reasoning. Now, this is a major open problem, but our work and previous work on unprovability of these n to the cubed, n to the k size circuit upper bounds is progress towards this bigger meta-complexity goal. With that, let's cover some prior work. First, Cook and Kryajek in 2007 gave conditional unprovability results for these types of circuit upper bounds. Then, in a seemingly unrelated development, Sontham and Williams gave lower bounds against uniform circuits that can be printed out by efficient algorithms, right? And then there was a flurry of lovely papers by Kryajek, Oliveira, Bizdovsky, and Mueller giving unconditional unprovability of circuit upper bounds in theories of bounded arithmetic. And the way they all work is they execute this lower bound argument of Sontham and Williams inside one of the formal theories from bounded arithmetic. It's kind of an indirect way to use the inherently constructive nature of these theories to get these unprovability results. Now let's talk about our results. So we unify, simplify, and extend nearly all the previous results. So here's a precise statement. For example, for any fixed k, VPV does not prove that P is contained in size n to the k. P is these fixed size circuits. For any fixed k, VAPC1, which corresponds to randomized efficient reasoning, does not prove that ZPP with an NP oracle is contained in size n to the k. So that's zero error randomized time, and also it can decide SAT for free. And then finally, we also show a very pointed theorem that says efficient reasoning cannot distinguish between non-uniform and uniform expressibility. So, and that goes for both VAPC1, the randomized theory, and VPV, the deterministic theory. So in the particular case of VPV, it says that, look, this theory cannot prove that simultaneously NP is easy for easy for circuits and hard for algorithms. Essentially, these theories must bundle together the computing power of algorithms and circuits. So how do we get these simplifications and unifications? Well, we don't reason inside the formal theories as previous work does. Instead, we exploit the witnessing theorems to convert that existential quantifier over circuits into uniform circuits, and then we kind of throw that over the wall and we prove new uniform circuit lower bounds against the precise notion of circuit uniformity that comes out of the witnessing theorem. And doing that, we both make the proofs of previous results easier and more modular, and we get these new results. Okay. So for the remainder of the talk, we're going to go over uniform constructions of circuits, and then we're going to do a cartoon proof sketch of one of our theorems. So uniform circuits. Start with a Turing machine, give it as input 1 to the n, and as output, you will get a circuit that on n-bit inputs computes the desired function, f on n bits. That's the standard notion. The notion that comes out of provability in VPV is learn uniformity with equivalence queries. An equivalence query is an oracle where if you have a circuit and you want to know if is this a correct circuit for the function f on n bits, you feed it to the oracle, and it will either answer with a counterexample, a specific n-bit string such that the circuit gets that string wrong compared to f, or it will say, yes, you've got the right circuit, good job. Using this, we can define the following uniform circuit complexity class of learn EQR uniform size S, where you can think of the computation of these machines as a tree that starts from an initial state, asks an equivalence query, and then continues on with computation. And importantly, any valid sequence of answers to these equivalence queries leads to a correct circuit. And you can see that this is a depth R of n tree. Now let's go over our methods for VPV in particular, which again are going to directly transform uniform lower bounds for learn uniform circuits into unprovability results. Suppose that VPV proves P has cubic size circuits. Call VPV as efficient deterministic reasoning. Then we have a formal object, a VPV proof of those circuit upper bounds. We hit that with VPV witnessing to obtain a Turing machine. This is for each function in P that on input 1 to the n can ask a constant number of equivalence queries and then always outputs a circuit on n bits that decides f on n bits for any function in P. So this is what we get from the combination of witnessing with our assumption that VPV proves P is contained in cubic circuit size. Here's an example of one of our technical contributions, a uniform circuit lower bound. For every fixed k, P does not have learn constant query uniform n to the k size circuits. Therefore, this machine cannot exist. Therefore, this proof cannot exist because we know the VPV witnessing theorem is true. Thus, VPV does not prove P has cubic sized circuits. That is our proof sketch. For each type of unprovability result that I showed before, we have an accompanying uniform circuit lower bound against learn uniform circuits. Please see the paper for those results. They are somewhat complicated to state. Let's now go to open problems. First, it would be amazing if we could show P versus NP is independent of VPV. And currently, this might be possible because Pick and Sonthunum recently showed that VPV does not prove very strong circuit lower bounds. We showed that VPV and other related theories do not prove circuit upper bounds. Currently, our theorems do not match up, but if one were able to show that VPV does not prove weaker circuit lower bounds, or show that VPV does not prove stronger circuit upper bounds and make these theorems match, then that would be progress towards the independence of P versus NP from a very expressive and interesting theory of bounded arithmetic. Now that's a major open problem. So let me also state a nearer term open problem. We could also want to show that VAPC1, the theory that corresponds to efficient randomized reasoning, does not prove for any fixed k that ZPP, zero error randomized polynomial time, has size n to the k circuits. And this should follow pretty directly from improving our randomized learn uniform circuit lower bounds. Thank you very much for your time, and I hope that you will read the paper and send me any questions you have. Thank you.